The next talk is by Carolyn van der Bogert, Ages of Geological Units in the Schrödinger Basin Context for PRISM CLPS 2024. Go ahead, Carolyn.
Okay, so let's get going here. I wanted to, in the scope of, because of the PRISM CLPS selections, to have a look at the ages of geologic units in the Schrödinger Basin to give a context for whatever mission was selected, or missions were selected, or instrument packages were selected to be delivered there. And so let's just really quickly look at the background, because of course I needed to go back and look and see what do we already know. We know that Schrödinger is the second youngest basin, lunar basin. It had originally been mapped as being late Nectarian by Wilhelm's 1979. But he later observed some the fact that there aren't any superopposed Nectarian aged craters, and basically moved it then to be between the Imbrium and Oriental basins. So that moves it into the Imbrium period. Carolyn et al. On the large SPA map that she presented at a poster yesterday also places it into the lower Imbrium due to its morphological characteristics. So we have various geologic units in the basin that we also would like to know something about the age of. The basin materials, there are some light plains unit, the sort of purplish or this pinkish unit that's mapped here. Dark plains, very small little bits of what are mare patches that were observed now later than in this original mapping by Wilhelms. They're naturally the dark mantle deposits, the vent materials that everyone is very interested in. And there are overlying Eratosthenian crater materials, as well as possible secondaries from the Oriental Basin. So what do we know about the absolute age of the Schrödinger Basin? Well, MEST had a look at crater size frequency distributions using the Hartmann chronologies and suggested that the basin might be Nectarian based on the fact that it exceeded the Imbrium chronology line in his plot at the smaller crater diameters. But the craters that are larger than this actually are below the Imbrium line. I miswrote that here. And so basically, I think the interpretation here is maybe that here probably we have an effect of secondaries from the Oriental Basin, and this could push the age determined for the younger craters to a somewhat older age. Also, we have work from Neukum and from Orgel et al. Orgel et al. Worked on the data set that was generated by Facet et al. In 2012 and basically fit ages both cumulatively and differentially using a new correction. And she gets 3.86 billion years, and that's consistent with what Neukum got for an age of the crater. Now you notice as we continue on in a few slides with adding ages that I have added a little timeline in the upper corner that you can follow along the sequence of events. So, but first I want to review what do we know about the ages of these units. And so what do we know about the dark mantle material? Well, Shoemaker et al. In 1994 looked at the area using some high resolution Clementine data and basically interpreted it as being as young as Copernican, so anywhere from 2 to less than 1 billion years old, based on observation of the crater diameters that were in equilibrium. Okay, and then comparing that with other work to get an estimated age. MEST also looked at this area and estimated an age of 3.2 to 2.5 billion years, using Hartmann's chronology in the same form as that figure that I showed earlier, and comparing this to the relative ages of the different units. So that's what we know previously about the dark mantle. The light plains had been measured with a crater size frequency distribution in 2013 for a study of light plains units to get at the origin of light plains. That's this red area that's marked here in this map. And the dark plains were also looked at in the MEST and Shoemaker works as being mid-early to late Imbrium, or about 3.2 billion years in the same, using the same estimation techniques. So what we wanted to do now was to look at these units all using one technique. We wanted to use the Neukom et al. Chronology and update the existing Hiesinger measurement because we have access to that CSFD, of course. And then we wanted to do new measurements on the dark mantle deposit as well as the dark plains materials. And so these are our count areas that we are using for this study. And these are constrained, for example, based on image availability and wanting to have consistent illumination angles, etc. Okay, so what are our results? When we update the light plains age from the Hiesinger et al. Data set, we get an age of 3.81 billion years. And this CSFD is well fit with one with one isochron of the production function, which suggests that this is one discrete event. Then we looked at the dark mantle deposit using TC data to look at the northwest flank of the vent, and we determined an age of 3.7 billion years. Then looking at the dark plains, this was rather difficult because some of the little patches gave us CSFDs that could not be fit with an age, and others exhibited equilibrium like this one that I plotted here. But what we can say from this plot is that because the equilibrium condition extends to larger crater diameters than the age that can be fit for the pyroclastic deposit, that this Mare deposit is likely older than the pyroclastic deposit. So we can at least get a relative age for that. So out of this compilation of data and our new measurements, we're able to give a formation sequence where the basin forms first, the deposition of the light plains happens, the Mare happens sometime in between the light plains and the dark mantle deposit, and that was all wrapped up by about 3.7 billion years. So to say a little bit more about the interpretation of the light plains, what are their origin? I mentioned that the CSFD is well constrained, and so this indicates a single discrete origin. It postdates the Imbrium basin. It's somewhat too young to really be considered as Schrödinger and breccia deposits, and so this is actually seems to be consistent with materials delivered by the formation Orientale, which also has an age of 3.81 from the Orgel data set. And this would also be consistent with the stratigraphic relationships in some of the geologic maps. What can we say about the dark plains and the Mare deposits? Well, they superpose the light plains deposits. And as I mentioned, they're in equilibrium at larger crater diameters than we can fit the vent CSFD. And so they're going to be older than pyroclastics. And so this is a bit older than the MEST interpretation. And then finally, the dark mantle deposits, our result is giving an age that's much older than these previous results. The MEST data set, however, only measured 19 craters, and our data set contains 69 that are actually fit, and many more craters in the smaller diameters. And the Shoemaker work didn't actually use a lunar chronology to fit their data. So I think that we can be confident that we have a pretty robust new age. Now, given the time, I just wanted to very briefly mention that we had also done measurements in the Apollo 17 area to compare the whether we could actually measure a CSFD on pyroclastic deposits that would give us an age that's consistent with the radiometric age of the orange glasses collected there. And indeed, we could do this. And so we feel that this previous study supports our ability to get a robust age for the vent. And this points to all of the units in the Schrödinger basin having formed in the Imbrium period. And this, of course, then has implications for the cold traps and the ages of the cold traps where you might find volatiles that were erupted at this location. So thank you very much.
Thank you. Thank you, Carolyn. Excellent talk. In fact, I'm going to update my talk in real time based on your information.